So here we have a multivariate optimization problem with what at first sight looks like one constraint. So we're having a simple linear function here, 2x plus 4y. That's the function which we want to maximize. We call that f. And we want to maximize that subject to a constraint. Let's call that g. And that is 14 minus 4 times x to the half minus 4 times y to the half. And you know, of course, x to the half and y to the half, that's just square root of x and square root of y. And you would immediately know, if you have a function like this, that as a what you need is that x is larger or equal to 0 in order to calculate the square root, and also y is larger or equal to 0. So we would have perhaps, restricted the domain to these values. Now, really, if you have square root functions, you could calculate square roots of negative numbers, but then we're dealing with, we need complex numbers, okay, which we're not really dealing with. So in some sense, it's best to solve this by acknowledging that we have two more constraints here. You can do it without this, but I want to show you how that would work. And so we basically just call these two more constraints. We'll call the first one h of x and y, and that is just x larger or equal to 0. Remember, if we apply the Lagrangian method, we want our constraint functions to be formulated such that they are larger or equal to 0. And we'll use a third one, let's call it here p of x and y, and that is that y is larger or equal to 0. So these are basically two more constraint functions we are dealing with. Altogether, we are having 3 constraints. And perhaps what you can already see here, what we do here, actually, let's use a little bit of color coding. We have the blue constraint, that's the g, and let's give ourselves a gray constraint and a green constraint. Okay, the green constraint is that y is larger or equal to 0. So basically, y we have on the vertical axis, x on the horizontal axis, so that y is larger or equal to 0. That's really the constraint down here, and we need values on that line or larger than that line. Then we have the gray constraint, which is that x is larger or equal to 0. That means this is basically this line, this boundary, and we need values of x larger or equal to 0, so we need to go into this direction. And I forgot that arrow, the green one, so we need values in up here. And then the blue constraint is indeed that square root function, 14 minus 4x to the half minus 4y to the half. That is basically this function here. So that's the boundary of this function, and we need values below that line. Okay, they will be allowed by this g function. Okay, you could figure that out by solving that for y, for instance, and you would have y on the left hand side and smaller or equal than something on the right hand side. So we need values below here. So the gray area is our allowed area, the sum of the 3 constraints. And you can perhaps already see that this constraint is going to be compact. The combination of these 3 constraints is going to be compact because we're having all the boundaries are part of it, so they're closed. It's a closed constraint when taken all together, and it's bounded because we could easily draw a circle around all of these allowed values. So it's bounded and closed, and that means it's compact. And that combined with a continuous function means that we already know that there is a solution to the problem. Now, think of that function f of x, that's just a linear function, so in 3 dimensions it's a plane. Now, a plane, of course, will not have a maximum. So here it's the constraint being imposed, which will deliver a solution. So, as we want to apply the Lagrangian methodology, let's write down the Lagrangian function. So that is L of x and y, and then Lagrangian multiplies, and I leave some space here for the moment. So then the function, so that's 2x plus 4y, and now our constraint term. So we're having a Lagrangian multiply, and I call that lambda g because we're using that's the Lagrangian multiplier to the g constraint, and then 14 minus 4x to the half minus 4y to the half, then plus the next constraint, the h constraint. So we're having Lagrangian multiplier, but I call it lambda h, times the h function, that's just x, plus lambda p times the p constraint, that's just y. So this is our Lagrangian function. So let's complete that here. We're having 3 Lagrangian multipliers. So I'm just slightly squeezing this in here. And our necessary conditions, which any solution has to meet, are the following. The partial derivative of L with respect to x has to be equal to 0. I'll complete that in a moment. I'll just write down what we need. Partial derivative of L with respect to y, that has to be equal to 0. I'll write an equal to 0 once we have that completed. And then we need, for each of our constraints, we have the constraint, so we need g of x and y needs to be larger or equal to 0, and we need that lambda g, the respective Lagrangian multiplier, times the constraint is equal to 0. So that's the complementary slackness condition. And we're having 3 of these because we're having 3 constraints. Okay, so let me just write all of these 3 down. So there's a multiplication sign here, is equal to 0, and the third constraint is p. Of course, we know that h and p are really just the constraints that x and y should be non-negative, but treating them as a formal constraint will actually show us how to find the final solution, because otherwise it's not straightforward. This makes finding the solution easier. So let's go back to our partial derivatives of the Lagrangian function. So the partial with respect to x is just 2 from here. Then here we have lambda g minus 4x to the half, so that is minus 2 lambda g x to the negative half. And then we have here another x, lambda h times x, so we have plus lambda h, and there's the last constraint doesn't have an x, so that doesn't appear. Then the partial with respect to y, there we have a 4, and then we have minus 4 lambda g y to the negative a half, so that's minus 2 lambda g y to the negative a half, and then we're having the last constraint which involves the y, so that's just lambda p. And of course the necessary conditions mean that these two have to be equal to 0. So these are the Lagrangian necessary conditions. Any solution has to meet these. We already know, because the combination of our 3 constraints is compact, that we will find a solution. So that's just nice to know right from the start, because otherwise you would always have to contemplate not finding a solution. So what do we do? Well, first, just try, and you know that we are now separating. We are separating our solution method into looking for solution in different areas. The first one is that we are looking for an unconstrained solution. Okay, and that is where we set all of the, well, we say that all of the constraints are slack. So that means we're setting all of the lambdas to equal to 0. That makes our Lagrangian necessary conditions a little bit easier because all the lambda terms fall away. And that means that we get from the first two necessary conditions, we get 2 is equal to 0 and 4 is equal to 0. Of course, that is impossible because 2 is not equal to 0. So that means there is no solution. No solution here. And remember, our function is just a linear plane. We know that if we don't impose a constraint, that there is no solution. So you could have, told this right from the start, but we'll just done it formally. So that means in that gray area here, in the shaded area, we won't find the solution to our problem. So now we'll be looking in 3 different areas. Let me just separate this out. We're looking in the blue, on the blue line, on the blue boundary. We'll be looking on the green boundary and on the gray boundary. Okay. So let's start looking at the blue boundary. Let me just separate this out here. So we're looking where lambda g is larger than 0, but for the moment we will restrict lambda h and lambda p to still be equal to 0. So we're basically saying we're looking at positive values for x and y, and we're looking on that blue boundary. So if we do this, what happens to our equations? So the lambda g term survives, so we get 2 minus 2 lambda g x to the negative a half is equal to 0, and 4 minus 2 lambda g y to the negative a half is equal to 0. And what we also get is, so now we have 2 equations, but we have 3 unknowns. We have x, y, and lambda g, so we need a third equation. Where does that third equation come from? It comes from here. Okay, and in particular from this part, if we set lambda g to larger than 0, so if this part here is larger than 0, then we know that the product, for the product lambda g times g to be equal to 0, we know that g needs to be equal to 0. So from our inequality constraint, we can isolate, we are only looking on the equality, and graphically we are looking for values on the line. So if we take our g constraint and just look at the equality, we get our third equation, 14 minus 4x to the half minus 4y to the half is equal to 0. So now we have 3 equations and we have 3 unknowns. So let us solve that from that first equation. So one way, a typical way that delivers a straightforward solution is we're isolating the lambda g from the first and from the second equation. So we get an equation lambda g here from both these equations, and then we can set the right hand sides equal to each other. Okay, so that's sort of a typical way of how to deal with this. So in our case, what we do here is, if we bring the lambda g over to the other side and then divide by 2, so you can immediately divide by 2, that means you get 1 minus lambda g x to the negative a half, but we basically get lambda g is equal to x to the half. Okay, so that's what you get from here. And from that second equation, you get lambda g is equal to 2y to a half. I see we have a 4 here and here 2. That's where the 2 comes from, because divided by 2. 4 divided by 2 is 2. So now we can set these two equal. So we know that x to the half is equal to 2y to the half. Okay, and now we can basically substitute this into the third equation. Okay, we can substitute that into the third equation. So for instance, you can replace x to the half here with 2y to the half, and then you get an equation only in y. So I'm not going to go through all the algebra here. What you get from here is that you get a y value of 1.3611. Once you have the y value, you have the x value, because you know how x and y are related to each other. The x value is x is equal to 5.4444, and actually you can also calculate the lambda g, because if you have either x or y, you can calculate that, and the lambda g in this case is equal to 7/3. So let's call this point A. Okay, let's call this point A. And let's see where that is. So x is 5.4, 5.4 is about here. So that point is about here. That is point A. Okay, and what we also need to know is, what is the function value at that point A? So you just take these two values for y and x and plug them into the function. And once you do that, you get a function value, and let me abbreviate it like this. Function value at point A, and the function value is 16.3333. Okay, so this is our first potential candidate solution. So are we finished? Do we know that this is the solution? Well, remember, the Lagrangian conditions are necessary conditions, not necessarily sufficient conditions. They would be sufficient conditions if the constraints were concave and the function was concave. Now the function is a linear function, so the function is actually concave. Okay, the function is concave. But if you look at the constraint, and we see it here graphically, you can see it already, that is not concave. And of course you could establish that the constraint G is not concave by calculating the Hessian of the constraint, and you would find that that is actually not negative semi-definite everywhere, which would be the requirement for it to be concave. So the necessary conditions are not sufficient, they're only necessary. That means we need to continue. If they had been sufficient, then we would have known that if we have 1 point, that's a sufficient condition. So if they're not sufficient, we need to keep on going. So let's look, and let me change the color so we know on which boundary we will be operating now. Let's operate on, so to say, on H. So if you think of, let's draw another line here so we know where we are working. So let's operate on H. Okay, on h, we know that x is equal to 0. We need x to be larger or equal to 0, but on the boundary line, x is equal to 0. Now we can make our life easy here, because you know that to if you think of the function here, if x was equal to 0, then you know that the function increases with y. So you would want the largest possible y. So we already know that if we are looking on this boundary, where we are ending up is going to be that point up here, the largest possible point. And that is the point where we are not only on the gray boundary, but we are also on the blue boundary. So on that point, we are having lambda h larger than 0, but we are also having, and I should do that in blue, lambda g larger than 0. The only thing, the only boundary we are not on is the p constraint, so we are setting that equal to 0. And you can see we can't at the same time be on all three boundaries. That doesn't work in this particular case. So we're now looking at that case, okay, and we know we're on this point, and we can already call it point B. Okay, we can already call it point B. And let's see what the algebra tells us. Okay, so in some sense we know the point already. We haven't quite calculated the coordinates yet, but we can do that basically in no time. So we're working here. How do our constraints look like if we only switch off the p constraint? We're saying we're not on p, so it means the lambda g and the lambda h survive. So we're getting from the first equation, we're getting 2 minus 2 lambda g x to the negative a half plus lambda h is equal to 0. The second constraint is 4 minus 2 lambda g y to the negative a half. And here we only have the lambda p, but that's 0, so that is 0. So now we have two equations, but we have four unknowns. We have x, y, lambda g, and lambda h. So that means we need two more equations, and they come from the g and from the h constraints. Okay, and it's the same pattern. If we are setting lambda g and lambda h larger than 0, then g and h have to be equal to 0. So we'll basically just use the g constraint, 14 minus 4x to the half minus y to the half, that has to be 0, and the h constraint is that x is equal to 0. X is equal to 0. And you can immediately see we have the first coordinate. X has to be equal to 0. Now, once you plug this into, so once you plug x equal to 0 into this equation, into the second constraint, we immediately see that 14, so from here then it follows that 14 minus 4 times 0, so that falls away, minus 4y to the half has to be equal to 0. When you solve that, you will find the y coordinate, and turns out here the y coordinate, if you solve that, what you get is y is equal to 12.25. So you can see that here, perhaps that coordinate here is 12.25, just above 12. So that point B is at x equals 0 and y 12.25. Now you can calculate the lambda values for this, what you actually find is that the lambda g is, where are we? Okay, so the lambda g, and we go here. So lambda g is equal to, and we had that equation up here, 2 times y to the half. Okay, so now what this means is that if y is positive, the lambda g is larger than 0. Now, next, if you then calculate lambda h, now what you will find out is that lambda h is equal to negative 2. Okay, and here I need to correct myself, but I leave that and I explain why I need to correct myself above, because hopefully it helps. It's one of the sort of tricky bits when you do have multiple constraints. So here you can see we have a lambda h negative 2 and lambda g larger than 2. So where I need to correct myself, if you're activating 2 constraints, as in this case here, what you actually don't need is that both constraints are larger than 0. So let me just actually take that away. What you need is that sort of a combination. I won't give you the exact condition here because it's not really important. You need them to be unequal to 0. Both negative isn't going to work, but that's sort of detail I'm not going to explain. Okay, but what you need them to be unequal to 0. Okay, and that activates the lambda h and the lambda g in these equations. If you're only activating one constraint, like for point A, then indeed that Lagrangian multiplier has to be larger than 0. But if you're having 2 Lagrangian multipliers, then you could get a combination. You either have both positive or at least one positive. Okay, so what we have here is the point x0, y 12.25. That is point B. And what we also need is what the function value at point B is. And if you plug all of this, if you plug x equals 0 and y 12.25 in here, well, you get 4 times 12.25, so we are getting 49. So let's actually add that here. The f at this point is 49. The function value at that point is 49. The function value at point A was, where do we have it, 16. So here the function value is 16.333. And so we already know from calculating that point B is superior to point A. It has a higher function value. It also meets the Lagrangian conditions, but it has a higher function value than point A. So there's a third point we need to look at, and let's color that green, and that's this point here. Okay, that's the point where the green constraint, that's the P constraint, and the blue constraint intersect. And we'll already call that point C. Now let's do that calculation here, and that is where we, and now we do it correct right from the start. I should that line here, where we have lambda P is unequal to 0, and the blue constraint also, so we're having lambda G unequal to 0, but the gray constraint, the H constraint, that remains 0. Okay, so that's now, that characterizes point, and we already know that there's only one point because there's only one intersection of this blue and the green line. So only one point, that's point C. Again, to get the coordinates, we have to write down our Lagrangian conditions with these imposition, so we're getting 2 minus 2 lambda g, so that is a 2 times x to the negative half is equal to 0. From the second, from this equation, we get 4 minus 2 lambda g y to the negative half, and now a plus lambda p is equal to 0. And then again the two constraints, 14 minus 4x to the half minus 4y to the half is equal to 0, and now the p constraint, y is equal to 0. So again, we immediately have one coordinate for point C, that is the y coordinate. If you plug that into the constraint, and you can see that's symmetric, so it's perhaps not a surprise to find when you calculate that the x coordinate here is 12.25. So that's that C point. Okay, and now we know what we need is the function value at that point. So the function value at point C, if you plug y equals 0 and x 12.25 into the function, so it's 2 times 12.25, that is 24.5 or around 25. Okay, so here the function value is 24.5. Okay, so we know we have 3 candidate solutions, A, B, and C, and amongst those, B is the highest. Okay, so this is our maximum point. This is our maximum point. This is the solution to the problem. So remember, as we are having altogether a compact constraint, we know we need to find a solution. We have 3 candidate solutions, and the best one amongst that is the solution. If that was not the case, you would have to figure out all across the domain whether there are any values larger than that. But we've sort of done that already, because the domain here is the blue line, the green line, the gray line. We looked at all those, and the shaded area. We looked at that at the beginning when we let all of the lambdas be equal to 0. We didn't find a point here. So we are all good. Now what I want to do at the end is I want to show you the actual function. Okay, so here we're having, so here's the actual function. That is the f function. That was 2x plus 4y. So that was f of x and y was 2x plus 4y. So it's a linear function. We're having, I'll make that a little bit bigger, the x here and the y-axis is here. See, the origin is here. Okay, that's where x is 0 and y is 0. So the origin is here. It's a plane, as we've talked about before. So, you know, by itself that doesn't have a constraint. That doesn't have a solution. But the we know that the solution here, the constraint, let me draw in the blue constraint. The constraint looks a little bit like this. Okay, so it's actually not too bad. The so if you think of cutting out the part of the function which is allowed by our 3 constraints, that was the green constraint, and the gray constraint was here. Okay, we're basically cutting out this part of the function, and we're asking, where is that function now largest? We found 3 candidate solutions. One was about here. That was the A candidate solution was about here. The B candidate solution was here. B, and the third candidate solution was here, C. Okay, and now you can perhaps see that here you can see very clearly that indeed the solution is B. Okay, that's where x is 0 and y is 12.25. Okay, that's the end of this example.